Good, good evening, my dear student. Today I am going to take a class on energy efficient and thermal away design of RAM on 3 FPGAs for digital signal processing. The topics today: overview, introduction, related work, energy efficiency, thermal analysis, conclusion, and the future scope of this research. Application of RAM in DSP. Application for CRAM are as a video frame buffer, computer main memory, or for stand alone signal processing. As data throughput uh, increase during DSP, the arbitrator built into the ASIC must prioritize access. Eventually, this will limit the data. Data throughput. A video RAM is a solution for this data bottleneck. Overview. There are many systems which use RAM as its primary memory. For example, ex- spacecraft or home computer, etc. Energy efficient RAM is even more important in outer space exploration as the power source is very limited and the environmental condition is extreme. Overview. Energy efficiency is not only based on the architecture of the system but also on the environmental condition. For that reason, low power RAM will increase the performance of the system even in extreme conditions. Introduction. In this work, we are going to create a RAM that aims to decrease the performance, the power using, and therefore make it more energy efficient. For serving the same purpose to make the RAM energy efficient, we are using low voltage complementary metal oxide semiconductor. The RAM, which is to be designed, designed is actually implemented on FPGA, which is field programmer gate array, which is an array of gate and can be used a per the requirements of a per programmer to alter its function accordingly. First FPGA used in our research. FPGA RTX 7 process technology 28 nanometer. RTX 7 in digital signal processing. RTX 7 devices provide high performance per watt fabric transceiver line rate DSP perform processing and integration in a cost optimized FPGA, the Xilinx RTX 7 family of FPGA as a peak DSP perform, performance of approximately Dmax per second. Ener- Energy efficiency with RTX 7 FPGA. Use the RTX 7 FPGA for implementation of RAM. We have calculated its overall power consumption, dynamic power consumption, and leakage power consumption by varying the values of output load and keeping constant frequency at 1 GHz and constant temperature at 25 degrees Celsius. Energy efficiency with RTX 7 FPGA. Output load 10 picofarad. Dynamic power 0.039 watt. Static power 0.078 watt. Total power 0.0117 watt. 100 picofarad. Dynamic power 0.185 watt. Static power 0.078 watt. Total power 0.263 watt. 1000 picofarad. Dynamic power 1.643 watt. Static power 0.080 watt. Total power 1.723 watt. Thermal analysis with RTX 7 FPGA. Use the RTX 7 FPGA for implementation of RAM. We have calculated its overall power consumption, dynamic power consumption, and leakage power consumption by varying the values of temperature and keeping constant frequency at 1 GHz and constant output load at 5 picofarad. Thermal analysis with RTX 7 FPGA. Temperature 26 degrees Celsius. Dynamic power 0.031 watt. Static power 0.078 watt. Total power 0.109 watt. 35 degrees Celsius. Dynamic power 0.031 watt. Static power 0.083 watt. Total power 0.114 watt. 45 degrees Celsius. Dynamic power 0.031 watt. Static power 0.092 watt. Total power 0.123 watt. Second, FPGA used in our research. FPGA Kintex 7 process technology 28 nanometers. Kintex 7 in digital signal processing. Next generation products with digital signal processor DSP technology and technology need to deliver more performance and versi- versatility than ever in less time for less cost and and consuming less power. Delivery more than 5,000 Gmax for fixed point and 1.3 teraflops floating performance system. Performance 7 series devices push the limits far beyond traditional DSPs in terms of total performance and per watt. Energy efficiency with Kintex 7 FPGA. Use the Kintex 7 FPGA for implementation of RAM. We have we have calculated its overall power consumption, dynamic power consumption, and leakage power consumption. By varying the values of output load and keeping constant frequency at 1 gigahertz and constant temperature at 25 degrees Celsius. Energy efficiency with Kintex 7 FPGA. Output load 10 picofarad. Dynamic power 0.039 watt. Static power 0.081 watt. Total power 0.0121 watt. 100 picofarad. Dynamic power 0.185 watt. Static power 0.082 watt. Total power 0.267 watt. 1000 picofarad. Dynamic power 1.643 watt. Static power 0.086 watt. Total power 1.729 watt. Thermal analysis with Kintex 7 FPGA. Use the Kintex 7 FPGA for implementation of RAM. We have calculated its overall power consumption, dynamic power consumption, and leakage power consumption by varying the values of temperature and keeping constant frequency at 1 gigahertz and constant output load at 5 picofarad. Thermal analysis with Kintex 7 FPGA. Temperature 26 degrees Celsius. Dynamic power 0.031 watt. Static power 0.082 watt. Total power 0.114 watt. 35 degrees Celsius 0.031 watt. Static power 0.093 watt. Total power 0.125 watt. 45 degrees Celsius. Dynamic power 0.031 watt. Static power 0.112 watt. Total power 0.143 watt. Third FPGA used in our research. FPGA Spartan 7 process technology 28 nanometer. Spartan 7 in digital signal processing. Both Spartan 6 and Spartan 7 provide dedicated DSP slice incorporating signal cycle hardware, multiplier accumulated max. In the Spartan 7 has DSP 48E1, which implements a 25 cross 80 signed multiply ar- architecturally. The DSP 48E1 provided in 7 series devices also enable the implementation of an algorithmic logic unit ALU and enables support of single in instructs instruction multiple data SIMD mode, which allows increased throughput. Energy efficiency with Spartan 7. Using the Spartan 7 FPGA for implementation of RAM, we have calculated its overall power consumption, dynamic power consumption, and leakage power consumption by varying the values of output load and keeping constant frequency at 1 gigahertz and constant temperature at 25 degrees Celsius. Energy efficiency with Spartan 7. Output load 10 picofarad. Dynamic power 0.006 watt. Static power 0.018 watt. Total power 0.024 watt. 100 picofarad. Dynamic power 0.024 watt. Static power 0.018 watt. Total power 0.042 watt. Output load 1000 picofarad. Dynamic power 0.206 watt. Static power 0.018 watt. Total power 0.225 watt. Thermal analysis with Spartan 7. Using the Spartan 7 FPGA for implementation of RAM, we have calculated its overall power consumption, dynamic power consumption, and leakage power consumption by varying the values of temperature and keeping constant frequency at 1 gigahertz and constant output load at 5 picofarad. Thermal analysis with Spartan 7. Temperature 26 degrees Celsius. Dynamic power 0.005 watt. Static power 0.018 watt. Total power 0.023 watt. 35 degrees Celsius. Dynamic power 0.005 watt. Static power 0.020 watt. Total power 0.025 watt. 45 degrees Celsius. Dynamic power 0.005 watt. Static power 0.023 watt. Total power 0.028 watt. Conclusion. All all this FPGA is the best architecture for low power design of any RAM on FPGA in case of total and leakage power consume- consumption. There is no change in dynamic power when we are changing temperature. There is no changing in static power when we are changing output load. Future scope. In future, we shall write very low code of heterogeneous architecture and circuits related to RAMs in very low. In subsequent research, we may use 16 nanometer process technology based ultra scale FPGA for design of RAM and other hardware. We have only applied capacitance scaling and temperature scaling to de- develop the low power design. In future we shall use different low power techniques. For example, voltage scaling, IO standard to develop low power design. Thank you. Any question? This is my RAM code in Verilog.